In this video, we're going to be solving a nonlinear system of equations by using the elimination strategy. So if you look at the problem in front of you, you can see that we clearly have a nonlinear system because this first equation has an x squared in it. And then you can see the second one is linear because it doesn't contain any additional functions. So we're trying to find where this quadratic and this line cross. And we're going to use the elimination strategy. And if you think back to when we first used elimination, remember our goal with the elimination strategy is to add the two equations together and to eliminate a variable. And if you think about the first couple of steps that we had to take, first we had to get the variable that we were choosing to eliminate on the same side of the equation in both equations, and then we needed to make sure that they had identical coefficients that were opposite signs. So one was positive, one was negative, so when we added them together, they would cancel. And if I look here, what I notice is that I have two variables. I have x and I have y. And if I look at x, there's a lot of x's in here. There's an x squared, there's an x, and then here's an x. And because there's an x squared and an x, you cannot choose to eliminate x, as it's going to get very, 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 very messy. But if you look at the y's, there's simply a single y here and a single y here. So if we can set this up for elimination, we can eliminate that y pretty easily. So because these y values are on different sides of the equation, we have to start off by moving one of them so that they're on either both on the right or both on the left. And it doesn't matter which one we move, so I'm just going to move this second one here to the other side. Again, it doesn't matter if you move them both to the right or both to the left, it just matters that they're on the same side. So here we have x squared minus 7x plus 11 equals y minus 1. And then I have negative x, which I'm going to actually align that underneath the 7. So I'm going to do negative x, then I don't have a number, so it's equal to negative y minus 4. So notice how I'm kind of aligning them up, and I can see what's on each side of the equation. Well, now that I look at these, I notice that the y's here, because I moved that one y over, are the same coefficient of 1, but one has a positive 1 and one has a negative 1. So what I can do here is I can add these two equations together. Now, the x squared doesn't add with anything, so I simply have x squared. Then these add together to be a negative 8x. I then have plus 11 equals, this y plus negative y becomes 0, and then negative 1 and negative 4 become negative 5. So what I can then do from here is I can add 5 to each side. So I then have x squared minus 8x plus 16 is equal to 0. So by using the elimination strategy and then doing some rewriting, I've set up my quadratic pretty well here to utilize any of my strategies. So you can use factoring a trinomial here, you can use completing the square, or you can use the quadratic formula. Now, while you can use whatever strategy you want, I noticed that this is a great situation to utilize the ABC factoring strategy because I have A equals 1, B equals negative 8, and C equals 16. And because A equals 1, I can use that quick little shortcut and say, okay, I need two numbers that multiply to 1 times 16, which is 16, and two numbers that add to negative 8, that B value. And if I'm thinking about it, two numbers that multiply to 16 but add to negative 8 are negative 4 and negative 4. So what I can do is I can take this quadratic right here, and I can now rewrite this as x minus 4 times x minus 4 is equal to 0 by using that ABC factoring strategy. And then from here I notice, well, I have zero product property because I have something times something equals 0. So I set both parts equal to 0. And I find, in this particular problem, by solving each mini equation, that I have one single x value of x equals 4, which is fine. Sometimes you have equations that only cross in one spot. So here for our solution is only going to be one single point with an x value of 4. And then what I need to do to find the corresponding y value, because remember we're finding the point where these cross, I'm going to plug this back into one of my original equations. And I'm going to pick this easier equation here because it just has less variables in it and it means less calculations. So if we take negative and then we put our 4 in for x plus y equals negative 4, So we have negative 4 plus y equals negative 4. Add 4 to each side. We get y equals 0. So I end up with a y value equal to 0. This tells me my solution is when x is 4 and y is 0. So let's use elimination one more time to solve the following system of nonlinear equations. So remember, our goal when we use elimination is to eliminate a variable as we add the two equations together. And in order to do that, we need the variable we want to eliminate on the same side in each equation. Now what I notice here is that I don't really want to eliminate x because I have a lot of x's here. I have x squareds and x's, and eliminating those is going to be pretty tricky. But what I also notice is that I have one single y in each problem, and they're already on the same side of the equation. The only detail I'm missing is the fact that they don't have opposite signs. And hopefully you're thinking back to when we've used elimination in the past, and you know that we can multiply equations, entire equations, through by a value in order to manipulate those coefficients to make them the same but opposite signs. So what I can do here is I can actually multiply this second equation through by negative 1. So I'm not changing this first equation here. That stays y equals 9x squared plus 6x plus 2. But I'm multiplying that second equation through by negative 1, so I have negative 1y equals negative 1x squared plus 8x plus 19. So notice I multiplied everything in here by that negative 1. And by doing so, I kept the integrity of the equation, but I've now set this up to utilize elimination. So if I add straight down here, I notice that I get 0 here because y plus negative 1y is 0 equals 9x squared and negative 1x squared is 8x squared. And then we get plus 14x plus 21. So I was pretty easily able to use elimination to eliminate that y variable right on out of the equation. Now from here what I can do is I can now utilize any of my factoring strategies. And because those coefficients are a little large, I'm going to utilize the quadratic formula. So I have x equals negative b, so negative 14, plus or minus the square root of 14 squared plus negative 4 times 8 times 21 all over 2 times our a value of 16. So now if we simplify this a little bit, we end up with x equals negative 14 plus or minus the square root, and we'll simplify that in a second, all over 32. So now if I focus on this part underneath the square root here, I find that that becomes a negative 476. And what you should automatically be thinking is that this negative underneath the square root is telling me that I have an imaginary solution for x, which is fine. We know that that's possible. That's why the imaginary number system exists. But when we're solving a system of equations, we're trying to find the point of intersection. And what we're really focusing on here are the real points of intersection. The imaginary ones, while we can solve for them, are very, very, very complex. So what you can do here is you can stop and you can say, well, because of this negative underneath the root, there are no real solutions, or there's no real points of intersection to this particular problem. So for the system problems only, you can pause when you find a negative underneath the square root, and you can say there are no real solutions where these two equations will cross. The way that they're graphed, they will inevitably miss each other, and they will never actually intersect.